T-lock seat design. This demonstration was performed for Greater Vancouver District in mid-January 1992 and witnessed by engineering and operations personnel. The valve was placed on the test stand and pressure tested to 150 psig. In addition to the seat adjustment, Pratt demonstrated the ease of an in-field seat replacement. A new seat was installed and injected within 20 minutes without any additional adjustment required. This test head was brought up to pressure and there was no indication of leakage. The valve was opened to determine the seat area to be destroyed. Prior to destroying the seat, a small area of elastomer was removed to illustrate the valve could sustain damage without leakage. Once completed, operation instructed Pratt to destroy the seat, causing severe leakage. This illustrates the amount of rubber removed without leakage. Additional elastomer was then removed, causing leakage with only head pressure. Once the test vessel filled, the pressure increased, creating increased leakage to a level at which typical butterfly valves would require seat replacement. This stream across the 24-inch valve was approximately 15 feet. Once the damaged area was determined, the local injection kit was used to inject epoxy between the existing hard epoxy and elastomer, returning the seat back to its original position with the disc acting as a mandrel. This method is permanent and will provide consistent, uniform contact between the disc edge and seat. The possibility for human error is eliminated. This procedure took 1 minute and 6 seconds. Once the injection is completed, the needle can be removed. The seat has been permanently returned to its original position. This is the final amount of elastomer required to be removed to create this type of leak. Considering the seat is recessed in the body with only a maximum of 0.25 inches protruding into the flow path, this type of damage is extremely remote due to the fact the seat is recessed in the body and in the relaxed state. Once the valve seat was adjusted, it was immediately tested to 165 psig and the test indicated bubble tight shutoff. The following day, the valve that received the new seat was replaced in the test stand and pressurized to 175 psi. The valve was bubble tight with pressure on the flat side of the disc, which is a more difficult test. The valve did not require any seat adjustment after installation. The conclusion reached by engineering and operations was the Pratt design offered simplicity in seat adjustment, a reduction in potential damage, and the ability to adjust when other designs would require complete seat replacement. You can depend on Pratt experience.
This video presentation demonstrates how easy it is to adjust the seat of a Henry Pratt Triton XR70 butterfly valve. This procedure was performed by a member of our marketing staff who had no previous experience with our local seat adjustment. We begin by manually closing and then pressurizing a 24-inch Triton butterfly valve to 150 pounds per square inch water pressure under the disc to simulate typical field conditions. Air pressure is applied at the valve's maximum design pressure. Notice there are no air bubbles, demonstrating the valve is leak tight. Though Pratt valves are designed for many years of reliable service, repairs occasionally are required. Since we know it is important that downtime due to equipment failure is minimized, Pratt has developed a method that allows our rubber-seated ball valve and Triton butterfly valve seats to be adjusted or repaired in line under pressure. Watch now as a segment is cut from the E-lock seat to create a leak. The Triton's seat configuration consists of a patented rubber E-lock seat which is installed in a channel that is machined in the inside diameter of the valve. The seat is installed in the channel and then secured in place by injecting epoxy during assembly. The valve is now manually closed and repressurized. The valve begins leaking extensively where the seat was cut. Pressurization cannot be achieved. The technician prepares the local injection equipment. A pre-measured 2-part epoxy compound is mixed. The epoxy is then poured into the grease gun. The grease gun is assembled and purged of air. The valve is repressurized, showing the leak caused by cutting the rubber seat. While the valve is still under pressure, the technician greases the tip of the hypodermic needle and then inserts the needle between the seat and epoxy. The epoxy is injected when the grease gun is pumped. The epoxy will travel around the circumference of the seat until it reaches the void. As the epoxy nears the void, the water is forced to flow through an increasingly smaller area until the epoxy reaches the damaged segment and seals the opening. With the damaged area now repaired, we are able to repressurize the valve to its design maximum. Despite significant damage, we are able to return the valve to leak tight by local injection. The kit, which requires no cleanup, consists of a needle, a coupling, and a 24-ounce grease gun. This kit is supplied with a 2-part epoxy compound and is readily available through the Henry Pratt Parts Department.